Have you ever wondered why time ticks slower for a speeding car than for a stationary observer? Welcome to the enigmatic world of relativity, a theory that challenges our everyday understanding of time and space. Imagine the universe as a stage which we perceive as three-dimensional space. Now, add time as the fourth dimension and you have the fabric of the cosmos, also known as space-time. Relativity, in essence, tells us that this space-time isn't rigid. It bends, stretches and warps in response to mass and energy. Picture a trampoline sagging under a weight. That's what planets do to the fabric of space-time. And here's the kicker. Moving objects, including light, follow this curved path, giving rise to what we perceive as gravity. Similarly, the faster an object moves, the slower its time ticks. It's a mind-bending concept, isn't it? Albert Einstein's theory of relativity redefined our understanding of time and space, making the impossible seem probable. Einstein's special theory of relativity, proposed in 1905, revolves around two fundamental ideas. These two ideas are the postulates of the special theory of relativity. The first postulate is that the laws of physics are the same for all observers in uniform motion relative to one another. This means, whether you're sitting still in a stationary train or moving in a train at constant speed, the laws of physics apply equally. You can't tell if you're moving or stationary based on the physics happening inside your train. The second postulate is that the speed of light in a vacuum is the same for all observers, regardless of their motion or of the motion of the light source. This is quite a mind-bender. Imagine you're standing still and seeing a beam of light pass by. Now imagine you're racing alongside that beam of light at half its speed. According to our everyday intuition, you'd expect to see the light beam moving at half its original speed, right? But no, Einstein said, the light beam will still zip by at the same speed. These two postulates lead to some peculiar conclusions, namely time dilation and length contraction. Time dilation is the idea that a moving clock, or any process that measures time, will tick slower than a stationary one. So if you took a round trip in a super-fast spaceship, you'd come back to find your friends on Earth have aged more than you. Length contraction, on the other hand, is the idea that a moving object will appear shorter in the direction of motion. So if you were to observe a spaceship flying by at near light speed, it would appear squashed. The special theory of relativity, therefore, presents a world in which time can stretch and space can squeeze. Welcome to the fascinating universe of Einstein. Einstein didn't stop at special relativity. A decade later, he introduced the general theory of relativity. Now let's dive into the world of gravity. The general theory of relativity takes us a step further, embracing the effects of gravity. Here, Einstein gave us an entirely new perspective on this ubiquitous force. Instead of viewing gravity as a force pulling objects towards each other, Einstein proposed a radically different idea. He suggested that massive objects like planets or stars cause a distortion in the fabric of space and time, which we perceive as gravity. Imagine a trampoline with a heavy ball in the middle. The ball creates a dip, a distortion, and smaller balls rolling on the trampoline naturally move towards the bigger ball. That's a simplified way to picture it. This brings us to a mind-bending concept: gravitational time dilation. Time, according to Einstein, is not constant. It can slow down in stronger gravitational fields. So if you were to stand on the edge of a black hole, not recommended by the way, your watch would tick slower compared to a watch back on Earth. Your time would quite literally slow down. In the realm of the general theory of relativity, gravity is not a force, but a curvature in the fabric of space-time. This dramatic shift in perspective has reshaped our understanding of the universe and continues to guide us in our quest to unravel its mysteries. The theory of relativity is not just an abstract concept, it has real-world implications. This profound idea forms the backbone of modern physics, influencing technologies we use every day. For instance, the accuracy of GPS systems heavily relies on the principles of relativity. Moreover, relativity shapes our understanding of the universe's evolution, providing insights into the cosmic dance of galaxies and stars. So the next time you check your GPS or gaze at the stars, remember the genius of Einstein that makes it all possible.